Thank you very much for inviting me to give this lecture here in your academy. And thank you very much for that nice introduction. Actually, I will not speak about our space experiments today, but rather a little bit about the theoretical modeling work that I'm doing lately with Dennis Höning of the Potsdam Institute of Climate Impact Research, who is basically a tacit co-author of this presentation. Actually, I was asked to speak about plate tectonics, and I thought that it might be fitting, for this academy that we're talking about plate tectonics in the context not of geology and geophysics, but more in the context of astrobiology and what would we expect, if we found a second Earth. And the question that I was asking is, could the Earth have siblings that look different, or would a second Earth necessarily look like ours? And I think that is an interesting question, to pose and to discuss. And that is what Dennis and I have been working on and are working on. Now, you are, mostly from astrobiology background, as in astrobiology or astro-related subjects. So it will not be very surprising for you if I say that Earth is an exceptional planet. As we can see here, when we compare the Earth with its neighbors, Mars, Venus, and Mercury. And it's clear, even in this artist's representation, it is apparent that the Earth is different. So we have a lot of water, we have continents, we have life. And as you know, Earth is located in what is called the habitable zone. And therefore, it's considered to be habitable as it is. Of course, when we look at in the solar system, searching for life, but beyond the solar system, people are interested in another Earth. This is a great driver of the search for exoplanets and astrobiological research. Now, here is an interesting or a nice cartoon of the Earth's interior, highlighting plate tectonics and a few things that we know about this exceptional planet. It's the biggest rocky planet in our solar system, a little bigger than Venus, not much, but still. The compression is by 30 degrees and so forth, but this doesn't interest us so much in this context. In this context, what we are talking about is that this planet has something that the other planets in the solar system do not have, and this is active plate tectonics, continents, and so forth. A rigorously convecting mantle that is being shared, we believe, with Venus and Mars, but the plate tectonics is something else. In addition, we have a magnetic field and a dynamo in the core. We have an hydrosphere, atmosphere, and we have life, and we have feedbacks, of life to atmosphere surface interior processes probably. So the Earth as such is a complicated system where everything, depends on each other and fits together. And of course, we cannot discuss the whole thing in one talk. This is a lecture series if that would suffice, but we talk about some of the aspects of this. Now, talking about plate tectonics, this is a map of the surface of the Earth. And what you see here clearly are the continents standing about 3,000 and more meters above the datum of the ocean basins. And then you see in the ocean basin, you see that, for instance, this mountain chain, volcanic mountain chain, the mid-Atlantic ridge, and other mid-oceanic ridges as well, like here in the Pacific, or here, beneath the south of India, and which is an important element of plate tectonics, as we will see. In addition to that, we have troughs. Where the ocean is particularly deep, and where we know that oceanic plate is subducting underneath the continental plate. This is here, at the west coast of South America, but we have more complicated subduction zones in Asia, and actually here off the coast of the east coast of Asia, we have very complicated tectonic systems where not only we have subduction underneath continents as we do here, but subduction underneath oceanic plates, for instance. And here is a cartoon, from the USGS. I'm pretty sure you have seen that before, where the elements of plate tectonics are collected. Here is that mid-oceanic ridge where material, from deep in the mantle comes to the surface, pushes the lithosphere aside, introduces volcanic lava that solidifies as basaltic crust and pushes the plates to the side. And then you have subduction zones here underneath a continent, like we have in the west of South America. And in these subduction zones, when the plate is subducted, there is partial melt. The plate is melting, and that melt is descending and adding to the continent. So this is the region where continents actually grow. And that will be a focus of our discussion today. But in addition to that, we have other subduction zones like this one here, where the oceanic plate is subducting underneath another oceanic plate, but still, there is melting and there is, volcanic activity. There are island arcs that are often then pushed against the continent and make a continent growth by that. And of course, we're pointing to the continents that are in the focus of our interest today. Now, I'd like to compare a little bit, very superficially, but plate tectonics with the other mode of tectonics in the solar system, that is stagnant lid tectonics, which we believe is, acting on Venus and Mars, and other more common objects in the solar system. So here we have plate tectonics. We have the ascending, material from the mantle. We have the melting of basalt, the production of basalt, production of basaltic crust. We have the continental crust. We have here the subduction underneath an oceanic plate. And if you do a finite amplitude convection calculation like Claudia Stein and others did, you can see that this can occur in their calculations if certain conditions are met. What is much more common, these calculations, is something like that, where you have a cold plate sitting on the convective system, and the heat is not, brought up to the surface through rising convection currents, but rather conducted through the plate, to the surface. And this is what we see here. There is the heat, the convection currents, and then you conduct the heat out, through the lithosphere, onto the surface. There are, of course, every once in a while, there is a volcano where heat is piped through, but it's not the same as, with plate tectonics. Now, it's not clear that the Earth always had plate tectonics. This is a hotly debated subject in the geology of the Earth. There are, a significant number of people that believe that in the Archean, there was no plate tectonics, but tectonics was different, and that it was sort of in between, on the transition, from a stagnant lid mode to a plate tectonics mode. We're not modeling this in this talk, but something that you should remember. Here is another aspect of the comparison. On the left-hand side, you have a 3D calculation, spherical shell of stagnant lid convection. You see that cold plate, on top, and then the advection of heat underneath. And this reddish is a hotter temperature than this greenish bluish temperature colors here. And this is a plate tectonics, or at least mobile lid convection, where the surface is included, in the convective flow. And you see already by the colors that this planet here cools, much more rapidly than that planet to the left here. And this is shown, in this this plot on the right-hand side, where this has been done by Doris Breuer, where the mantle temperature as a function of time for a plate tectonics planet is compared with one with stagnant lid. And you see that the plate tectonics planet cools much more rapidly than the stagnant lid planet. And also when you look at the energy that is removed from the interior, then the plate tectonics planet removes much more energy over time as compared with the stagnant lid planet. So, this mixing of the cold stuff with the interior is an efficient way of losing heat. And this is why, the Earth, mantle cools much more rapidly, and why, behind the reasons why the Earth cools the core and has an active dynamo and produces a magnetic field, and Venus doesn't. This is one of the consequences of that. Now, if you discuss the habitability of these planets, then you can ask yourself the question, we have life on Earth. I mean, would a Earth with a stagnant lid on top be habitable? And we've looked at this question, and others have done that as well in a number of papers between 2017 and 2019 at the latest. We looked at the degassing of a stagnant lid Earth and Tosi et al. 2017. Then Mareike Gotthold and Dennis have looked at the greenhousing of the atmosphere and that. And we found that the stagnant lid planet would have an ocean, but the ocean would only be about a few hundred kilometers thick. Most of the water, the inventory of water would stay in the mantle. But the outgassing of CO2 and of water would still allow that surface water to be stable and make that planet at least habitable in the sense of allowing surface water, water on the surface of the planet. However, many agree that for life, and maybe it's for complex and evolved life, that plate tectonics is at least useful. And part of that reason is that you recycle near-surface rocks and volatiles with the planet's interior through subduction and volcanism, and that helps to create geologic diversity. For instance, the granitic cratons, the continents that we have, are of course, nice balconies on which life, can sit in the sun and harvest, solar energy. That's much better than, doing that from the interior of an ocean or even from a continental shelf. Although in the continental shelf, you're better off than you are in the deep oceans. Also, plate tectonics replenishes depleted surface rock as the base for the nutrition chain. And with the carbon silicate cycle that you probably all know about, that plate tectonics helps stabilize the atmosphere temperature in that cycle of the Earth over long timescales. Which is important, for the evolution of life. You need stable conditions. And then plate tectonics cools the deep interior and helps generate a magnetic field, which, could or can protect life, from harmful radiation from space. So plate tectonics is useful in this sense. There's also some, interaction, of continents and bio activity. So for instance, I've talked about that already. Bioproductivity on continents is significantly larger than in oceans. You can see that here, the blue color is where, where the bioactivity is low. These are the deep ocean basins. And then greenish is, where bioactivity is comparatively large. Of course, we have the deserts, but then, we have lots on the continents where we have the green color. And then, of course, the continental shelves, where we have water, but I mean, the water is not deep, and there you can still harvest, photons and do photosynthesis. Bioactivity, on the other hand, enhances the weathering rate by up to a factor of 2 of that, and that is important, in the evolution of the continents. So the erosion of the continents, as you will see later, is an important element of the cycling of the crust. Also, microbes act as catalysts in the formation and metamorphism of hydrous minerals, which is, again, an important element. We won't talk about that too much, but in the transition or the transport of water into the interior, the smectite to illite transition, for instance, can matter. And then let me say that the continental surface area has been almost constant, for the past 500 million years, although that is debated. And here I show you a compilation of the many models and discussions of, the evolution of continents. You'll see that this varies quite a bit, from the early work of Armstrong, who believed that the continents, you have to look that backward, grow rapidly in the beginning and then stay constant most of the time, to others, where you had a slower growth and then small growth, in the past 500 million years or something like that, or, other that, like Hurley and Brand, that have growth, much later, and growth would be ongoing at the present time. Now, an interesting new study by Guo and Kuranaga, based on argon isotope data, supports actually that early continental growth and reports something like an Armstrong model. And actually, in a way, the models that I'll present you are somewhere between Armstrong and Belousova, apparently. It is pretty difficult, from a theoretical point of view to make models like these here work, but somewhere in between here is what you can actually do with plate tectonics and convection modeling. Now, let me talk about the way you produce continental crust and about 2 cycles, in addition to those many other cycles, chemical cycles that are happening on the Earth. And I'm talking here about the crust and the water cycle. So you produce continental crust by, and I said that already, by melting, partial melting sediments together with oceanic crust, together with mantle rock, in the presence of water. So water reduces the melting point, and then you form partial melt here, and that is erupted through volcanoes and adds to the continental crust. And then you have erosion on the continents, and that feeds back into that sedimentary layer. So you have a cycle of continental material, through erosion and production of continental crust, and that cycle is closed. And because you need water here to melt this material, you are linked to the water cycle. And the water cycle works like this. You degas water from the mantle at the mid-oceanic ridges into the oceans. Then you precipitate and transfer water to the continents and, wherever. And then water is subducted along with the sediments and the oceanic crust. It sits both in the sediments and in the oceanic crust into depth, in hydrous minerals, for instance, or in pores. And when these minerals break down, the water is released, and then you form this melting here and continental crustal material. So you have these 2 cycles that are closely linked together and that depend on each other. For the continental cycle, through the water that you need; for the water cycle, through the sediments that help you subduct water. And what we do here in this modeling is we consider these cycles together with a model of the thermal evolution, the cooling of the Earth. Now, why is the water so important? The water is so important because it has important effects on the physical properties of rock. And one is here on the left-hand side. You have the melting temperature. This is the liquidus of rock. This is and these here are the solidi of rock, for different concentrations of water. So if you're saturated with water, the melting temperature is much reduced, and then depending on the concentration of water, it is not as much reduced. But in any case, I mean, water, even in small, sorry about that, in small concentrations, reduces the solidus and allows, partial melt in the mantle and in subduction zones. And the other important thing is that, when you look at the viscosity of the mantle, if you add, I mean, this is the dry viscosity profile of the mantle, increasing with depth due to pressure, and then increasing towards the surface because the temperature decreases, the viscosity is temperature dependent. But if you add water, you see that you reduce that viscosity profile. So adding water to the mantle will reduce the viscosity and therefore increase the speed at which the convective engine is working. So that is very important. These two aspects are very important. Water helps to increase the speed of the convective engine, and water allows melting. Now, let's now look at subduction. We've looked at this type of subduction underneath the continents already. We talked a little bit about that, subduction underneath oceanic plates, but there's also a mode of subduction, when that occurs on continents. So it is possible that continental lithosphere subducts underneath continental lithosphere. And that is a region that is not so important for the production of continental crust, although you have folding of mountain belts and so forth. But it is a continental margin that needs to be considered in our considerations. Now, here is a model that we use. We represent continents by spherical shells, and then we look at the margin between the continents and the oceans as a function of the fraction of continental coverage. So when we grow the continents to grow on the sphere, the Earth sphere, we study how these their boundaries would evolve, and then we say that the total length of the convergent plate should be constant, because that should be determined by the properties of the mantle convection underneath. So when we look at these boundaries where oceanic crust subducts under continental crust, which is particularly important for us, we see that this increases with increasing coverage, continental coverage of the planet, up to a maximum at 40%. And that is actually what we have right now at the Earth. So the Earth is in a state, where the length of their ocean continent margin is maximized, which is an interesting observation. We also take then that that initially, we don't have continents, and therefore we have only ocean subduction, but that is reducing as a function of time as we're transforming from this here to that. And then, when we further grow the continents, then we don't have any room for much for oceans anymore. So this type becomes important, and that increases then as well. So we have this transition from starting out here, going through there, and then with an increasing share of this type of continental margin also in the game. Now, when you look at these cycles and study them, you see that there's actually positive and negative feedbacks in it. I try to explain that to you with both the continental cycle and the water cycle. Let's start at the continental cycle. So we have a surface area of a continent given. Then this continent is eroding, and the weathering and the erosion is proportional to the surface area of that continent. So that is then subducted together with water, and is brought then in this subduction zone where it melts and produces continental crust. So it adds to the surface area here as well, which then increases the erosion. You subduct, and then you increase the surface area as well. So that is a positive feedback. And this cycle is linked to the water cycle. So we have a given water concentration in the mantle. That water concentration affects the convection speed. If you increase it, the convection speed increases. This increases the rate at which that stuff is brought down. So it increases the suction rate of sediments in water. You gain water, you add that to the water concentration, you increase the convection speed, and so forth. So another positive cycle. And these positive cycles are linked. Now they're balanced by two negative cycles. If you have a surface area, you're weathering, and then you have a loss of continental crust. And part of it comes back through the sediment, but part of it is just accumulating at the bottom of the ocean. So there is this negative cycle. Also, when you look at the water concentration, through the mid-oceanic ridges and partly also through those volcanoes, you lose water and it goes into the atmosphere and in the hydrosphere. So there is a negative cycle. And now it depends when you put the both together, what the relative weight of these are. Is the positive cycle, the positive feedback dominating, or is the negative feedback dominating? And this is what we have in our model. So we have three coupled first order differential equations with the rate of change of mantle water, the rate of change of the mantle temperature, and the rate of change of the continental surface area. And I don't show you the equations here. If you want to know the details, you should consider, for instance, this paper here. So we have three state variables: the water concentration, the temperature, and the area, or the volume of the continental crust, or the area of continental coverage. I mean, if you assume that the continental thickness is constant. And these three variables span a phase space. Now we're looking at a plane in the phase space at the present mantle temperature. So we have the continental coverage in percent. 40% is the present Earth, 100% would be a planet where everything is covered with continents. And then we have the mantle water concentration from no water in the mantle to 200 ppm water in the mantle. And what we have at present in the Earth is somewhere in between here, what's observed. And you see that these are the arrows, how the system evolves. And then if I go further, I can draw lines of where the rate of change of the continental surface coverage is zero. That means that production and destruction are in equilibrium. Okay, so that the continental crust does not grow along this line here. And you see that starts out with at zero mantle water concentration, the equilibrium. Then the continents grow. You have increased sedimentation. You have to balance that by increased production if you want to have a zero here. That you can do by putting water in the mantle, and therefore the water in the mantle increases along this curve. And also, can play this game for the mantle water concentration, and you see that with increasing coverage, I mean the length of the subduction zones decreases, and therefore the mantle water concentration decreases, and all the water is accumulating on the surface. So the water goes to the surface, and here the continental crust grows. And then there is an equilibrium point, which we call the fixed point, and this is what you do in this type of mathematics. And this is where the system actually tries to go. And you see that, you see that from looking at these arrows, where we start off somewhere, with a combination of values, and we are always, evolving towards that point here. Now, I can tell you that what we have to do here is actually with a bifurcation system. So we have a one single fixed point if the negative feedback is dominating, and that fixed point is actually stable. So if you look at it from a point of view of stability, you see that everything is going towards that fixed point. And then you have a bifurcation parameter, and that we have only schematically here, and that depends for our system on the ratio between water carried by sediments and the oceanic crust. It basically is a measure of the importance of the sediments in that system. Now, if I increase my bifurcation parameter, come into that regime, what will happen? And this is what happens. You find that now your continent as a function, metal water concentration as a function of continent crust is multi-valued. So you actually have three fixed points. Now here, you have the same game as here. You increase, with in equilibrium, you increase the water concentration. But now the sediments are so important that actually the sediment transport, increases, because of the sheer size of the continent, so that you don't need the water concentration anymore. But now here, the length of the subduction zone has increased, and now you need to balance that again by an increase in the mantle water concentration. And then the mantle water concentration does this thing. Well, that is quite similar to that here, so nothing particularly new in here. But the new thing is that now you have these three equilibria, and of these here and these here are stable. But this here is actually a metastable, a saddle point. Now, so, the conclusion is that the Earth, which is at that value of continental coverage, at that value of mantle water concentration, is sitting in a saddle point and not in a stable situation. Now, you don't have to be concerned because the system is very, very slow. You can sit here for quite some time, without rolling down to that or either that direction. But it is important to note that the Earth is not in a stable equilibrium, at least according to this theory. And actually, we did a stability analysis, a very extensive stability analysis, to show, that the Earth would actually be in that situation. Now, there are processes at work, through, for instance, life that can stabilize the situation here. But anyway, from the point of view of mantle convection, this is what it is. Now, there's an interesting consequence of that, and that has to do with the stability of the continental surface area. If you looked at a system where, the negative feedbacks would be dominating, then you can see how, as a function of temperature, the fixed point would evolve, and this we've plotted here. So you see that the fixed point would actually, in a cooling mantle, decrease towards smaller continental coverages. So this here is the present day, so that would come from here, say, down to here. And that would actually mean that the continents, trying to get towards equilibrium, should actually not be growing, or should actually not be remaining constant, but should decrease in their size, which has never been observed. Nobody has ever said that the continents are actually shrinking. However, in this model here, where you have where the positive feedback is dominating, what's happening is that the stable point up here would also decrease, and this point down here would also increase, but the unstable or the marginally stable point where the Earth is sitting, this one over here, stays the same, stays constant at the same continental coverage for, at least for the 1700, 1600 Kelvin that we've looked at here, was actually going for a larger array of continents. So the stability of the continental surface area is actually an argument supporting the idea that the Earth is in this metastable equilibrium point. Now, we looked at the effect of life on that, and we took life to be affecting the weathering rate. So we compared an abiotic system where the weathering rate was reduced by 20% to a biotic system, and it would, basically do the same. However, the biotic activity would actually, reduce the continental coverage by about 10% or something like that. But it would sort of stabilize, the system in that situation. Now, here is a evolution, calculation that shows, how the fixed points in the phase planes and the actual system would evolve over time, starting with some initial conditions that we choose randomly from a box of initial conditions over 4.5 billion years. And you see that, the phase plane starts with one fixed point, actually in a stable situation. Then, as a function of time, these lines here change, and then the three fixed points develop, and the Earth is actually attracted first by that fixed point up here, but then as this one comes in, it sort of happens to get here and stay at that. But if we started differently, this is what happens. And now we're looking only at the phase plane at the present time, so at this thing here. And we're starting with a much broader range of initial conditions. And you see we're covering everything, from almost this fixed point down here to where the Earth is, to that fixed point up here. And what you cannot really see much here is, but the density of points, is up here, is about 90%. So from choosing randomly from initial conditions, about 90% of the systems end up in that stable fixed point up there. Another 10% end down here. They do not reach that fixed point down there because the temperature is so low and the amount of water concentration is so low that they never reach it for kinetic reasons. And only a few percent, end where the Earth now is. And here is the box, where we choose our initial conditions from. So we choose initial conditions between 0 and 200 ppm mantle water concentrations, between 2000 and 1800 Kelvin initial mantle temperature, and also the start of the subduction, varies between 0 and 2 gigayears. And we find that that solutions that can explain the present Earth, have to be on that brownish surface here. So it's a very peculiar combination. It's a large combination, but a peculiar combination of initial conditions that would actually get to the present Earth. Now, this also depends to some extent on the efficiency of heat transfer in the mantle. So this plane changes somehow, but the basic story, that the Earth is quite peculiar, is kept to that. So it's a tightrope walk here. So okay, what we can see is from that the Earth is quite peculiar as it is, with its a fine-tuned balance between volatiles in the interior and on the surface, with an atmosphere and hydrosphere, with about 50% from surface area, 20% of basaltic rock, and 40% or 80% in terms of volume of felsic crust. But the other planets, that one up here is actually much more likely. And this is a planet, that is almost covered to 80% with felsic crust, and where the volatiles are, mostly in the mantle. So it's actually more like a desert planet with an extreme climate. What? This one here is a planet where most of the water is on the surface and relatively little water is in the mantle. So these are the two extremes that are more likely than actually what the Earth is. So 90% versus a few percent versus 10% is what we're getting. But this here is the most habitable of the two. Now, let me close by showing you some of the latest things we're doing. We're now introducing the thermal blanketing of the continental crust, and that sets up another feedback mechanism, because the thermal blanketing of the continental crust, affects the temperature, and the growth of the continents will keep the Earth from cooling as much as it would without the continents, and therefore have a positive feedback on the continental and the continental crustal coverage and volume. And this is what we're actually getting out. Here we find that how the Earth is evolving. This is the phase plane where we have coverage, man and water, and potential temperature. And this is, for that, for a planet that starts at a lower temperature and that gets to that stable equilibrium point down here. And this is a continent, an Earth that almost entirely is covered with felsic crust, and where the temperature is actually relatively high. So the cooling, there's been a cooling, but then it warms again. Now this is a little bit extreme. We have to sort of fine-tune that, because in that extreme model we have assumed that the blanketing is such that there is no heat escaping through the continental crust, which is too extreme, admittedly. But again, I mean, there is the possibility we still get these three planets. We're not only getting an Earth, we're getting three different planets, in terms of the coverage with continents and in terms of their man and water concentration. And with that, I want to stop and thank you for your attention. And thank you very much, and I'm open for your questions.